Okay, in this video we're going to go through Chapter 1, Sections 3 to 5. So in 1.3, the title is An Introduction to Functions. So what is a function? And think of a function just as a rule. So a rule that assigns to each input quantity exactly, and this is important, exactly one output quantity. So the output is a function of the input. So functions can be represented using words. So for example, you can say in a given function as, I don't know, let's say height, as height increases, you can say height increases as age increases. So let's get rid of as. Okay, so I'm going to get rid of that. So you can say height increases as age increases. Okay, so age is the independent variable and height would be dependent upon age for its value. You can express a function as an equation. So here's the equation that you most frequently see, this style. Or you can write it in function notation. And this specifically tells you that y is a function of x because of this. Okay, so function notation is this one. And just regular everyday xy notation is this. And these are both lines, by the way. You can present a function as a table. So let's say you have x's and y's. And maybe you have 3, 4, 5 for your x's, and let's say for your y's, you have 2, 4, 6. Okay, so that's a function expressed as a table. And the last way you can express it is as a graph. So for example, if I'm going to do that line, I say that my y-intercept is 2, and the slope is positive 3. It might look like this. You would then be labeling your axes and you would be indicating, how you go up on your x and y axes. All right, so there's 4 different ways, words, equations, tables, and graphs, to express a function. Okay, so in terms of input and output, we can speak in the language of independent and dependent variables. So since a function is a rule that assigns to each input, remember I said this was important, each input a unique output. Outputs are viewed as being dependent, so depending upon the inputs. Writing a set of ordered pairs is this, okay? Will generally be in the form, so you'll have an input first, that will be your x. Output is y. Your independent variable, that's your x. Dependent variable, that's your y. And this is the generic xy. So know that your x comes first. It comes first alphabetically, and it comes first in functions because the input drives the train. So the input results in the output. So that, the old factory model of a function, you have x's come in, and y's come out. Okay, so that's your function. Okay, so sometimes when deciding which variable is the input and which is the output, it's not totally clear, but many times it is. So for example, if you have time is always going to be the independent variable. Time waits for no man, time marches on. You can see that that implies that time is independent of everything else going on around it. So we keep talking about functions, but we can also have relationships between variables. So when is a relationship between variables not a function? So these tables are going to help us determine that. So not all relationships define functions. A function is a special type of relationship, one where for each input, here's that terminology again, the rule specifies one and only one output. So look at this. Here's your basic function. Input yields one output, and there are no duplicates in the y column. Okay, now look what's happening for the next one. this is not a function, because if you put in 1, you can get out 6 or you can get out 7. So therefore, you do not have a unique output. So this scenario is not a function. Okay, the last one is a function, because if you put 1, you get a 6. So you don't get 2 outputs, you get 1 output. They happen to be the same output, but that's okay. So each input generates only 1 output. So even though the outputs are identical, you're not having an input generating multiple outputs. Okay, so that's an important distinction. So tables are one way to tell if you have a function, but a graph is another way of telling it. So the way we use a graph to determine if we have a function or not is through the vertical line test. So do you see all of these lines right here that are dashed? These are all vertical line tests, or vertical lines. So they are all, if you were writing equations, they are all x equal lines. Okay, so if there is a vertical line that intersects a graph in more than once, then that graph does not represent a function. All right? Because remember, the x's are your inputs. So if your input hits the graph more than once, then you'll get 2 outputs. And that's why the vertical line test is a good indicator of functionality. Notice in figure 1.12, here's a vertical line, and it's hitting here and here. So that is only a relationship, or a relation, and not a function. Okay, we're going to go through some of these algebra aerobics as well. Okay, so looking at problem 1 in algebra aerobics, which of the following tables represents functions? So remember, we're looking to make sure that each input gives me a unique output. So you have to kind of look carefully here, because what I'm seeing is my input for 2 gives me an 8, but my input for 3 also gives me an 8. So because I don't have a unique output, then I know I'm not going to have a function. Okay, so which of the following represents functions? So this is a no. Well, let me think about it. No, I'm sorry. I've lost my head. Let me just backtrack a little bit. Okay, so I have 1 output, even though they duplicate, it's okay. So this is a yes. Look over here now. Here's an input, and input for 2, I get a 7, but look, they duplicated 2, so it's not as obvious. You get a second input there. You get a second output that's different than the other one. Therefore, it is not unique. So this second table is not a function, because an input of 2 generates 2 different outputs. Okay? So remember, it's okay if you have an input, as long as you generate 1 output, you can have a second input generate the same output, and that is okay. But the second scenario, where I have a no written, is not okay. Okay, number 2. Does the following table represent a function? If so, why? If not, how could you change the values in the table so that it represents a function? So let's look. Oh dear. I have 1 several times, but I have 2 different outputs. So what should I do there? This currently is not a function, so this is not a function. How could I change it? What if I change the 1 to a 2? Now I have unique outputs and I have a function. So be able to change things so that you can get a function. Okay, refer to the table. The graph below is why a function. I'm reading problem number 3. And so I have a graph. So what test will I do? Well, I would do the vertical line test. And without even drawing them on, I can see that I'm never going to hit more than the function more than 1 time. Therefore, every unique line, aka every unique x, only gets me 1 y. Okay, so this is a yes. Okay, number 4. Which of the graphs in the next column represent functions and which do not? Okay, so let's look at these graphs. Now, graph A is kind of interesting. I only see one vertical line. Okay, so what does that mean? Well, if I only see one vertical line, then if I draw a vertical line on top of that, do I hit it more than once? Yes, of course you do. So this is not a function, not a function. This is a function. It's a parabola, which we're going to learn about later on in this course. And the circle, or I guess it's more of a ellipse, is not a function, because see how I'm going to hit one more than one place? So I have two no's and a yes in the middle. Okay, so then for number 5 it says, consider the scatter plot in the graph below. Is weight a function of height? Is height a function of weight? So let's see. What do I see? Height, right here, I'm going to fail the vertical line test if I go that way. But if I go the other way, if I turn this graph on its side, will I fail or pass the vertical line test? We have to think about this. It looks to me that height may be a function of weight. All right, so let's see. Is that going to work? So if I do vertical line test this way, I get two values. So that's not good. If I do it this way, looks like I'm going to have a problem here as well. So I would say that the best answer is no for this. So let me think about that for a second, but I think the best answer is no, not a function, either way. So I just checked the textbook, and we agree on the same answer. So number 5, no matter how you turn that graph, you have relations and not functions. And that was once again due to the failure of the vertical line test. Okay, looking at number 6, consider the following table. Is D a function of Y? So for D to be a function of Y, think about what you have to have. And then the second one is Y a function of D? Think about that as well. Okay, so let's think about 6 together. So for 6A, if they say, is D a function of Y? So that means that Y is the independent. So it can only give you a unique D. So look at the Y's. So 1992, you only have one unique answer. 93, a unique answer. Okay, so I would say yes to the first one. Now, is Y a function of D? So that means for every D, you can only get one unique Y. So look at the D's. Now look carefully, because look, there's 270 is twice, and you get different answers. So that's why the second B is a no, because I am putting the same input in and I'm getting a different output. So when it says, is Y a function of D, Y is your output. So is your output unique for every single D? And for B, the answer is no. Okay, so then 7, they ask us to write some equations. So write an equation for comparing a 15% tip in a restaurant. Does your equation represent a function? For computing a 15% tip. Okay, so to get your tip, you would say Y equals 0.15 of your X. That looks like a function to me. How much would the equation suggest you tip for an $8 meal? So if you do the math, you should be getting $1.20. And if you compute a 15% tip on a total check of $26.42, you should be getting $3.96. Okay, so make sure that you're able to get those answers as well. Okay, so we're going to go on in 1.4 to discuss the language of functions. So function notation is something that you want to be comfortable with and aware of. So when a quantity y is a function of x, you can say y is a function of x. Okay, so that's how you would say it, or write it in a big sentence. Or we can say y equals f of x, so that's a verbal abbreviation. Or here's the math abbreviation, which you're going to see quite often. So y equals f of x. So your output is your y, your input, and one way to remember it is your input is in the parens. Okay, so what's your dependent variable? Your dependent is the y, and your independent is the x. So x drives the train. Okay, and this is nicely summarized for you right here. So if you're going to find output values, that's also called evaluating a function. So make sure that that expression is understandable to you. So if you want to evaluate this r of x function at x equals 10, that means that you replace your x with 10 for every occurrence. And in this situation, we would get an answer of 31. So applying the function rule, r, to the input value of 10 gives us an output of 31. So the function rule is your equation. Okay, that's your equation in the box written in function notation. So very, very important. F of x does not mean f times x. It does mean the function f evaluated at x. So that is huge, and that is a point of confusion for many a student. So make sure that you are clear about that and that you understand that yourself. Okay, so here's more examples of evaluating functions, and I have a comment to make about your graphing calculator. If you know you have to evaluate a function numerous times, what I would suggest that you do is in your y1, put in 2x squared plus 3. All right, and then go to your table. And then what you're going to do is your table is going to give you the x's and the y's. So you want to look when your x value is, let's see, we'll go in order, -2, 0, and 5. And you will see the table that your graphing calculator provides gives you those answers. This also shows how you can do it by hand, which clearly you have to be comfortable with. Okay, example 2 asks you what is the value of the input. So they're going to give you an output, and you've got to work backwards to get the input. So look at this and be aware that you are finding x, which is the input. Okay, so for B, to find an input value for x that results, you're going to solve this equation. So here's another example of how to do it. So let's say, for example, let's just say that you have a graph on your graphing calculator, and we'll just say it's a line like that. Okay, if you know that your value, if we know your value is, let's say this is, I don't know, we'll just say this is y and this is x. If they give you this 7 here, and they want you to figure out this, what you would do on your graphing calculator is figure out, I'm going to draw another line right here, and I want to see the intersection, because where they intersect, I can then get this question mark. So algebraically, you would do it this way, as they've shown you in this solution to problem 2. Graphically, you're looking for an intersection. In any event, you will get the exact same answer. Okay, so now let's look at tables and graphs a little bit more. Example 3 says, using function notation with data tables. So use table 1.6 to fill in the missing values. So let's see. This is telling me my inputs. The inputs are in parentheses. So they want to know when the input is 0, what is the output? So the output is right here at 0. What if the input is -1? Your output is 1. What if the input is unknown, but the output is 4? Here's your output. Now, this is kind of interesting, isn't it? Because my output appears twice. So my input could have either been -2 or +2. So this last one has two answers, -2 or +2. Okay, and then they go on to look at the example using function notation with graphs, and you're doing the same thing. So for example, use the graph in this figure right here, and you want to estimate the following values. F of 0. So what does that mean? F of 0. You plug in a 0, and that's going to be right here. Okay, where across is the y-axis. And it looks to me like that's a 2. Okay, next one. F of -5. So if your x value is -5, which happens, looking at this, the hash marks on the x-axis are all 5s. They go up by 5s. So therefore, I'm going to go up here, right here in this general area, and I'm going to approximate that, and that looks about 1.5 on the y-axis. Okay, and the last one, they say that if your value is 0, what are your inputs? So your output's 0, what's your input? Well, there and there, those are the roots of the parabola. We're going to learn about those. So in both cases, the absolute value is 10. One is +10 and one is -10. But those are indeed the roots or the zeros of the parabola. Now on this page, they talk about rewriting equations using function notation. This is going to allow you to use your graphing calculator. So you're basically turning any equation they give you into a y equals equation so that you can put it in your y1. So this is your basic algebra. So make sure you are comfortable with these steps. If you want to isolate your y on the left-hand side, you have to use your PEMDAS and your rules of algebra to do it correctly. So look at these steps. They're all itemized very nicely for you. Make sure that you understand those and that you can internalize those. Once you have your equation in this format, you can then put it in your y1, and you can either look at your table or you can look at your graph. So that's the nice thing about getting your equation in function notation in the form f of x equals, because that goes right in your graphing calculator. So make sure you get the steps in example 5 and you can do that algebra. Now look at this example, because this is a very important one. So remember I said you're going to aim to put your equation in function notation so that you can use your graphing calculator. Well, you have to follow your algebra rules when doing that. So if you have this equation, y squared minus x equals 0, and your goal is to get y on one side, look what you have. You have y squared on one side. When you take the square root of both sides, you have to introduce this plus and minus. Because, for example, 25, if 25 is your y squared, isn't the square root either +5 or -5? Because -5 times -5 gives me 25, as does 5 times 5. That's why you have the plus and minus. The second you see you have plus and minus, you have two outputs to one input. And this is what happens. You fail the vertical line test. So you can either see it with your table or you can see it with your graph. The graph is very clear that I have the sideward facing parabola, which fails the vertical line test and therefore is only a relation and not a function. Okay, in this section right here, they're talking about domain and range. So you've got to remember that domain is your x's, so those are your x's, and the range are your possible y's. So you can use set notation sometimes, but we're going to start using interval notation. So right here, that is set notation. So if I'm saying that x is greater than or equal to a and less than or equal to b, what I would do is I would use that notation. Whenever you see the box, that tells you you have an equality. Okay, as opposed to, look at this. X is greater than A but less than B. You are going to use a paren because that indicates that you can have values up to but not including A. So that is really critically important. You could have half open or half closed, depending on how you view life. So for example, if you say here x is greater than or equal to A, you have the equality, and x is less than B, you cannot equal it. You can come close to it, but you cannot equal it. And the last one, x is greater than A, greater than gives me a paren, and x is less than or equal to B, that gives me a box. So you have to absolutely know that interval notation is critically important. It is used all the time in math, and it's a very nice shorthand that I want you to become comfortable with. Okay, so here's a graph, and if I asked you, tell me what the domain is, you would say, looking at this, do you see you have these dots that are closed in? The closed in dots mean that you can equal that. So the domain is going to run from, let me see how I'm going to count this by 2s, 2, 4, 6, yeah. So 2, 4, 2, 4. So that looks like that's going to go from -4 inclusive all the way to, and this looks like 2, 4, 6, 7 perhaps. 7, and we're going to say that that's a closed dot as well. So therefore, we have a domain that is -4 to 7 inclusive. Okay, then let's look at the range. So the range, the lowest value that I can get to, and you always go from low to high, by the way. That is the convention. So the lowest value that I can equal is right here, and I'm going by 2s, so it's at -2. And then the highest value, going by 2s again, is going to be a +6. And that's how I would indicate the range. Okay, so again, that's interval notation. And the closed dots mean that you can equal that function. So what if, just for an example, I gave you a line, and I said that this was 4, and this was, I don't know, 2, and this was 3, and this was 7. And I put open circles here and here. I would therefore say the domain went from 2 to 7, not inclusive, and the range went from, starting low, -3 up to 4, not inclusive. So you see the difference between those two types of notation and what they indicate. Okay, so here's another example. We had just completed this. So look at what we have here for an answer and make sure that that makes sense to you. Okay, 1-5 is an important section also. So we have these figures, and they want to know, do you have maximums or minimums? So if you look at these graphs, I can tell you that right here at this x would be a max, and that means that the y value of that function is at its highest point there. Here is a min, this part of the function, or this part of that function, and that means that the y value there is at its lowest point. Okay, this is a function in the next example, and here for, looks like it is h of x, I have a max and I have a min. And you can identify whether the max or min as a coordinate pair of your x's and y's. Okay, so then they say, all right, when is the output of the function positive, negative, or 0? So we're going to be using interval notation here, so look at this carefully. They want to know when is h of x, and h of x is this second curve right here, when is it greater than 0? So always read it from the left. So look, right here at negative 25, it is not greater than 0 because it equals 0. So you have to use a paren to say that very, very close to negative 25, it is greater than 0. And it continues being greater than 0 until very close to 0. But notice, you cannot put a box there because when you have a value of negative 25 for your x, or you have a value of 0 for your x, your output, your y value, is not greater than 0. It is 0, and that's why you are excluding those two endpoints by your notation. And then continuing, so it's going to be greater than 0, starting again very, very close to 10, but not when it equals 10. That's why you have a paren. And then all the way up to where the function ends at x is 25, and you are including that value, so therefore you have a bracket. Okay, similarly, where is the function less than 0? So it's less than 0, which means that the y values are negative, between 0 and 10, not inclusive. All right? You don't want to include the endpoints because at the endpoints, the function value is 0, which is what the next question answers. So that is important. At values of 0 and 10, the output is 0. All right? So that's just a strict equality. Okay, this first one was a strict inequality. This is mixed. This is a strict inequality. Okay, so those are very, very important concepts, as is the next concept about where your function is increasing and decreasing. So we'll do that next. Okay, so this is going to be a difficult graph to completely analyze since you have all these little turns. So when we talk about where is the function increasing or decreasing, increasing is going uphill, decreasing is going downhill. So for example, let me just get you a different color. From 1980, so all here up to here, we are increasing. Okay, here we're increasing, and we're increasing at a decreasing rate in some regards. And then other places we are decreasing. Okay, so here we're decreasing, here we're decreasing, here we're decreasing, here we're decreasing, here we're decreasing. So you get the idea. As I said, this is a complicated graph to do this on, so we'll pick a different graph to give you more detail about how you would use function notation to describe a pattern of change. Okay, let's look at this function instead. This is a simple parabola. And I want to know, where is your function increasing? So I would say, okay, my function is increasing, and you're going to read your x to tell me about the y. Okay, so this is your y, this is your x. So my function is increasing from negative infinity, because the arrowhead's going off forever to the left, all the way up to, but not including, the x value of 10, because at 10, it is neither increasing nor decreasing. Then my function, so what we'll do is, let's do this in one color for increasing. So here we are increasing, all right? So this is increasing, and then once we increase, whatever comes up, goes up, must come down. We are decreasing here, but we're decreasing starting a little bit past 10 all the way to positive infinity. Okay, so that's how you denote increasing and decreasing functions. Notice that means your slope is positive where you have an increase. So slope is positive here, slope is negative here. Okay, where it's stationary right here, when it's neither increasing nor decreasing, the slope, interesting enough, equals 0. Okay, so if you were to draw a slope, a tangent line to any of those positions, your tangent line would have a positive slope here, a 0 slope here, and a negative slope here. And that indicates where your function is increasing, neither increasing nor decreasing, and then decreasing respectively. Okay, concavity is another important feature of a graph. So this indicates concave up. See the kind of U? This is concave down. Okay, so concavity is independent of whether the function is increasing or decreasing. Okay, it's not an indication of increasing, decreasing. It's an indication of the shape. So one way you can always tell, if you were to draw a tangent line, so that's a line that just touches one place, if your figure is concave down, that tangent line will always be above your curve. Okay, if it's concave up, look, if you're going to draw a tangent line, it's going to have to be below. If you try to draw one above, you're going to hit two places that will not be a tangent line. Okay, so this is concave down, concave up. So another example, this is concave down, concave up. Here, the first one, your function is increasing. So envision this shape like that on a graph. This is concave down, but as I go from left to right, which is how you read graphs, my y values go up. This one instead is concave up, and as I read from left to right, my y values that I would read off my y-axis increase. Look what's happening here. Concave down. If you're facing this way, as you go from left to right, your y values decrease when it's concave down. Concave up, your y values are still decreasing, but it's concave up. All right, so be able to distinguish between those two types of situations. And then there's one more page to talk about, and that's getting the big picture, and that'll be our last page for this video. Okay, I really enjoyed this example because it gives you a practical application of what we're learning. So if you have a cup of hot coffee and time is going to be marching on, so time is independent, okay, and the temperature of the coffee is dependent. The more time that passes without having an independent source of heat for that coffee, the cooler the coffee will get. So what's happening over time? Your coffee is going to decrease in temperature. However, it's not going to get below the room temperature because how would it? Okay, it's decreasing because it's taking in some of the temperature, or it's losing some temperature to the room. It can't get any cooler than the room itself. So what about the concavity of this? My function is decreasing, but this is always concave up. So that's kind of interesting. Okay, example B. A U.S. venture capital increased modestly but steadily in the mid-1990s. Okay, so you can see it's increasing steadily. It soared during a dot-com bubble in the late 1990s. Here it is. Okay, so it increased steadily here. Ooh, now it's soaring. It reached a high. It had a very sharp decline. And then it started to recover, but then not so much. So you can see how the graph tells a story. Okay, and the last one's a neat one as well. It's a simple predator-prey model. So what do we have happening? What's happening initially? Initially, the lion population and the gazelle population are starting here and here. So the lions, as the lions begin to increase, how are they getting fed? Well, they're eating gazelles, so that decreases. Okay, this is probably the carrying capacity of the environment. It can't handle any more lions, so the lions population starts to fall off. As the lions fall off, what happens to the gazelles? The gazelles can increase again. And then that pattern's going to continue on and on. So again, graphs can tell us some very good information. They can tell us stories in a short, concise manner, and you want to be able to interpret what's happening with the function in terms of increasing and decreasing. Okay, the lions look concave down. The gazelles look concave up. So you should be able to talk about concavity, increasing, decreasing, and all those good things. And that's the end of the video.